1-hour talk, so it's partly a survey kind of talk. And Leon is one of the elder statesmen or philosophers of machine learning, who's worked in many areas. And again, and always has a very interesting take on the latest ideas.
Thank you very much. Thank you very much for giving me a chance to speak here and try to show some crazy ideas. So the title, in fact, I realized that I should have a better title. There was this one, but it's just for the Frenchies. But anyway, there's a work that's done by a number of people, and different parts of this work has been done by different people. Martin is a grad student in NYU. Sumit is an engineer in Facebook. David is a postdoc. Was a postdoc, now he's a research scientist, and he used to be a student of Bernard Scholkopf in Tübingen. Robert is here and was interning with us in 2015 when we started some of these things. Maxime is a long-time collaborator, was in France in INRIA, and we did a lot of work in vision. And Alex is a data scientist, is a behavioral economist with an experience in causation. So let's start by my motivations. Do not believe what they say in the newspaper. Machine learning is not a success. We can recognize objects in images, but we do that by training on more images than a human sees in a lifetime. It's a bit annoying. My son does that much better. We somehow can translate natural language with NMT, but are training on more text than a human can read in a lifetime. If you go to reinforcement learning, we can play Atari games, but this machine has to play more Atari games than any teenager, or maybe even a full classroom of teenagers. And for Go, it's a very big achievement, of course, but this machine has played more grandmaster level games than all of mankind. So obviously we're missing something, and when we want to go to the next step, like for instance, not recognizing objects in images, but understanding their relations, we wonder whether we're going to have enough data. And so the question is, what are we doing wrong? Are our learning algorithms inefficient? For the complex one, it's hard to say because we don't understand them well. For the simple ones, well, we are distinct like the Cramer-Rao bound that tell us that in the absence of a strong prior, we're not far from optimal. So prior, people say, oh, this is transfer learning. Humans do that fast because they can transfer across all the experiences. And we can do that in small, like we can transfer from computer vision tasks to other computer vision tasks. There are things we can do. But transfer learning equal all human experience is hypothetical. And how do I test that? How do I know whether it's true or not? It's not something we can test right now. So could there be something else? And so we decided to take another viewpoint and say, maybe there's more signal in the data than we think. Maybe we're just missing something important that's there and we didn't look at. And if you look at a typical supervised learning, or even a lot of unsupervised, except maybe ICA, we're going to look at the expectation of some features of the inputs, the cross of that with the outputs, but we're not looking really at all the moments that are in there. So there are a lot of moments that we don't really use. I'm going to give some examples later. And so if we go beyond correlations, you can ask questions about causation and questions about complex moments. And I hope it's going to be a bit clearer, but to give an idea, I was talking with Chris at lunch, and I had this observation, which is something that was a motivation for me. Like, if you look at a sentence and the structure of a sentence, let's say a parse tree, is the parse tree a good structure because it compresses the sentence very well? So is compression the real issue? Or is the parse tree a good structure because it allows us to manipulate the sentence? And I tend to go to the second group and think that the manipulation is something that's essential in the notion of structure. So the algebraic manipulation of the structure. And if you do that, you must have to consider that it's not about the sentences you see, it's all the sentences you could construct. It's all the manipulations you could do. It's about manipulating, so it's about causation. Because causation is a theory of manipulation. I'm going to come back to this. So in the first part, I'm going to review a couple of facts about causation and moments. And some of them, part of it is based on the work of Bernard and David Lopez-Paz, so, but I'm going to present it in a slightly different way. So what's the problem with causation? The typical problem is confounding. So suppose you have something like this. You have a variable z, let's say binary, for simple. And this variable has a positive impact on both x and y. So x is az plus some uniform noise, and y has a positive term, uniform noise, and a slight negative terms from x. So you have a system like this, and you force x to take a bigger value, you're going to decrease y. But if you only observe x and y, because they're all driven by z, they will appear positively correlated. So this effect is called the Simpson effect, and it's been the cause of many problems in medical sciences and other domains. So how does the scatter plot of x and y look like? So that's my scatter plot. So I have my uniform variables here. So basically I have two domains here. They're going down. That's the effect of C, the negative effect. And because it's binary, they're well separated. And when you look at a scatter plot like this, or something like this, well, there is a positive correlation, but come on, do you really believe that if you move x, you make x bigger, y is going to go up? No. And in fact, in other domains of science, when you get a scatter plot that has nice effects like that, well, the scatter plot gets your name. So that's a scatter plot in astronomy called the Hertzsprung-Russell diagram that shows the relation between stars' magnitude and luminosities. It's well known. And scientists clearly saw that, and they didn't think very hard. They decided, oh, these things are driven by other causes, and started making plenty of theories about the life cycle of stars and what they're doing and how they move in the scatter plot. So clearly, things that you can see on the scatter plot, not in the correlation, not in the mean or the correlation, but in the high-level structure, like you have two clusters and they're going down, is something important. It's a hint about causation. So if you look at causal problems with two variables, given two variables x, y, either x causes y or y causes x, or they have unobserved common causes, potentially confounding. They can mislead you, they can help you, or they're independent. And I'm going to follow the work of Bernard and focus on the first two, whether x causes y or y causes x, ignoring the rest for now. So that's an example again from Bernard. In this scatter plot, x is the altitude, y is the average temperature. Can you see something? Well, obviously, the altitude causes the temperature, because if I put a heater here, I'm not going to go up. So let's look at a simple example, additive noise, the works of Jonas Peters. Y equal alpha x plus beta plus some noise. So if x is Gaussian, the noise is Gaussian, you see an ellipse like this. Nothing to see there. But if x is uniform, now you're going to see something like this with sharp angles and a sharp cliff here and here in the distribution. And if you want to believe that, in fact, x was caused by y, so it would start this way, you should have to say that y is corrupted by some noise with a variable variance that happens to be just exactly right to create this shape. It's a bit of a coincidence, isn't it? So when you see something like this, well, it's a clear hint that y is caused by x and not the opposite.
Do you ever see something like this in reality?
Oh, yeah. I'll come to that.
Sorry, so what do you mean by high moment?
Well, the corners here, which are the important thing, just like ICA. In ICA, the corners matter. Here, the corners, or the cliffs that you have here and here, are telling you something about the direction of the causation. It's not for sure. It's possible that it's not true. It's possible that if indeed there is some strange noise that happens to create that thing, but you might even wonder why.
What I was wondering was, why are you calling that a high moment?
Because it's neither in the means nor the variances or the covariances.
Oh, that's what you mean.
So if you consider that the distribution is described by all its moments, it's in the high ones. Another example, suppose x is uniform, and y is created by applying this nonlinear function. Now y has a big peak here. So if you want to believe that y is caused by x, fine. If you want to believe that x is caused by y, you have to see a strange coincidence. How come y has a peak exactly where this function is flat? No reason for that, a priori. No cause for that. So this is a hint. So you could put a big catalog of these things, and it's not very interesting. What you can do is train a classifier. So how to featurize the scatter plot? Well, we know it's a matter of moments. So you can take the high moments, you can go in RKHS, or you can just learn features that are going to describe appropriate high moments. So the RKHS, that was David Lopez Paz's PhD work with Bernard. And then the learned one, actually, is a neural network. Well, okay, because it's fashionable to have a neural network these days. So you take all the points, you change them into a big phi vector, you average the phi vector, and you apply a classifier. Now, how do you train this? Well, how do we get data? Well, we're going to invent it. No. We're going to draw a distribution on X, draw, for instance, a number of a mixture of K Gaussian with a random number of elements in the mixture with random means and random variances. You're going to draw a transfer function by drawing a cubic spline with a random number of knots with random positions. You're going to draw a random noise with some variance that's uniform in a certain range, and you're going to add a random dependency with X so that it's not the same noise everywhere. And once you have this, you have a random mechanism. You draw a scatter plot, X, Y, and you say that's an example of X causing Y. You reverse the scatter plot. It's an example of Y causing X. And one thing we do sometimes is that you shuffle the Y's, and you say that's an example of nothing to see between X and Y. And, well, you train that. Sanity check, does it work? So the Tübingen guys have a data set of 100 pairs, things that they collected in the wild, like altitude, temperature, altitude precipitation, or edge of a shell and length of the shell, weight of the shell, diameter, displacement of the engine, consumption. Things for which we know the causal relation because it's non-physics. So we train this system with this random data. We apply it to that data, and we correct it with that one about 79% of the time, which is the state of the art for now. So sort of it works. It's a bit fishy as a validation if you think about it, because, okay, they were honest in the process of getting these 100 pairs and labeling them as X causes Y or Y causes X, but it's 100 pairs, it's not that much. In fact, my initial problem was about confounding, my initial example with the two scatter plots down. And you could do the same thing and learn whether a pair XY is suspicious and you must suspect confounding. Empirically, it works. But how do you validate that? What kind of data and what kind of experiment can I do that's going to convince people this is a good thing? I can tell you that if we run it, typically it finds bugs in the systems. When you have a kind of detects a confounding, very often you can trace back to some bug somewhere. So, but it's not a very scientific achievement. So we need something else. We need something that tells us from real data that we can find a causal signal. And best is to take something where it's unlikely to have a causal signal. So we're going to try to work with static images. I have a lot of image collections. People are working in ImageNet, Coco, and everything. And if you have an image like this, you could think about causation by asking some questions. What if I remove the cars? Can you imagine this image without the cars? Pretty easily. It's not very different, it just doesn't have the cars. What if I remove the bridge? Aha, now you need to remove the cars. It's asymmetric. So now can we use image data sets to identify the causal disposition of object categories? Like cars tend to be on bridges. Bridges, if the car's on the bridge goes away, these kind of things. So what do we have in this image data set? Well, that's a typical image data set. You have objects and bounding boxes. And we take the 20 classes of Pascal Vogt, but in the end we work with Coco because it's larger and we have 100,000 images to work with. I still have my problem with validation because I don't have the ground truth about what causes what. We have to invent something and do something indirect and smart to show that it's true. So typically nowadays we featurize the images, so we run some kind of convolutional networks and we get feature scores. So we use a typical state-of-the-art ResNet. We have 512 feature scores. We tried many of these. And there is something we know about the feature scores is that a lot of them are often interpretable as features of the scene. Like for instance, this is from Matt Zeiler and Rob Fergus, and you can see maybe that, well, there is a feature here that seems to spot the wheels of a car. And there is a feature here that seems to spot the presence of a person. And you can do these things. So we know that a subset of the features, at least, correspond to something real in the scene. So we're going to speak first of causal and anti-causal features. For each object category, so we have 512 features. Some of them might cause the presence of the object of that category. And some of them might be caused by the presence of object of that category. So, well, that's really the same thing here. So there are also some that could be the result of confounding and everything. It's too complicated. I don't want to deal with this. So basically, you have this situation. You have the real world here. And we have car, and we have the wheel feature. And we sort of assume that there is a causal footprint between these variables. Then we have all our recognition chain, the images, the pre-processing, and we have a scores for the wheel and a scores for the car. And somehow we have the hope that if there is a footprint here, the footprint is also here because these scores have been trained to follow what's happening here. Now, of course, it's to be proven. That's a working hypothesis. We can run our NCC filter. Remember, it's trained on artificial data, has never seen an image. It's just a black box, it's a classifier that's been built a priori, never seen an image. And we're going to train it on this course to identify the top 1% causal and anti-causal features.
So,
yes?
my first concern is what is causal. So, between cars and wheels, is the car cause of wheels or the wheels cause of cars?
It's presence. In that case, it's presence. The thing is that, well, there is a little trick. In a particular image, you can say that very often the presence of a car causes the presence of the wheel, because the wheel is attached to the car. If you remove the car, you can just leave the wheel. Now, the way we do it is that we reason between object categories. So we're not looking at the causal story in a particular image. We're looking at something called the causal dispositions of object categories. And that comes from the work of Mumford, who is a philosopher in Oxford, who tries to define the causes as the consequence of the disposition of objects. So this is what we're trying to do. The definition is intervention, but in terms of removing things. If I remove something from the image, what do I need to remove with it to have an image that's consistent and meaningful?
I remove the car.
You cannot leave the wheels.
And I cannot have a car without wheels. I mean,
That happens. Happens sometimes. There's a picture of a car in the Bronx. It doesn't have wheels anymore. So the disposition is that, in general, when there is a car, and if I remove the car, I probably have to remove the wheels. But if there is, let's say, a lamppost, if I remove the car, I can leave the lamppost. Well, listen, it's going to come together at the end. You'll see.
So NCC is still this thing where you generate random splines, right?
It's trained on random data. It's pre-trained before seeing any image. It's not going to be retrained ever. It's a fixed black box that we apply to the scores on this data set to decide. We're going to call this one, this top one, the top 1% causal and the top 1% anti-causal. Just a filter. Now there are other things you can ask about images. Like computer vision is not statistics. So you see the example in ImageNet, and this is a car too, but the context is wrong. And in fact, there is a kind of background story. In a little while ago, 10 years ago, a technique was called the bag of visual words. So they would take the local features, SIFT typically, or HOG, cluster them, and call each cluster a visual word. Then you see an image is a bag of visual words, and you apply the typical bag of words technique to decide what's in the image. And there was a little hope that if you look at the classifier, you could see, for example, which words were used by the car category, and then you could look at these words in the image and hope to see the car. Didn't work at all. Turns out that the detection for the car category uses features that are all over the place. Uses the context as much as the car itself. So there's no way to detect the position of the car using this. And this is why the computer vision people moved to the detection task, which is to find the bounding box as well. because they believe that classification is no good. You cannot distinguish the context from the objects. So we can also define another split of the features. Object features belong to the object. They're typically in the bounding box of the object. Context features, well, they're not in the bounding box of the object. And you can access this pretty easily. You just take an image and you look at the value of the features, then you blank the context, and you run that again, and you see which features have moved. Obviously, these are the context features. Or you can blank the objects, and you look which features move, and these are probably the object features. So you can define pretty easily, kind of normalizing these variations, some scores that indicate whether something is object or features. And now is the trick. We're going to make an hypothesis and try to test an hypothesis, that there is an observable statistical dependency between object features and anti-causal features. The anti-causal features are those that are caused by the presence of the object. Basically, if a feature is anti-causal, we say it's more likely to be in the bounding box. The rest, we don't say so. And the trick is that if we show that it's true, we've shown that our black box classifier trained on random data was actually able to say something. It was trained on an idea of causation. It's the same for all 20 categories, which are visually completely different. And yet, it's able to distinguish features that are more likely to be in the bounding box. So now we have a way to test whether there is signal or not. So all this complicated setup is just to test. In fact, the way we have to find causation from scatter plots are very bad. They're just two-dimensional. It's super noisy. Suppose you want to do regression, but you can only do regression with two variables. All of the variables are noisy. It's not very good. But this is what we know how to do. And that's the result. So what you see is the object score of the feature for the blue, the top anti-causal, and the top causal. And what you see is that the blue score is always above for all 20 categories, even though what distinguishes the blue from the green is something that has never seen an image, was trained a priori on completely artificial data. So this is about 2 to the minus 20 chances for happening by chance. So for us, it's a hint that even in something as unlikely as static images, there is some kind of a causal signal. It must be pretty strong because our method sucks. The images are full of biases. It's a very unlikely place for that.
So sorry, is it correct to say that only 2 of those guys are statistically significant, actually?
No. I'm saying something else. I'm observing that whatever, don't forget that this is the same classifier running on all these categories. It was trained only once, never seen an image. So the event that the blue is higher than the green for all 20 categories is not very likely to happen by chance.
But is the blue larger than the green?
Well, the blue is larger than the green.
No, not according to the error bars.
They're equal according to the error bar.
Well, even if you look at your empirical data, the blue is larger than the green on average. That fact that the blue is larger than the green in average, even not regarding the error bars, shouldn't happen over the 20 categories. Now, the error bars, they're quite large because it's very easy. I have 512 features. I'm taking the top 1% causal, top 1% anti-causal. Each one has 5 features. But the fact that I have this consistency on my 20 classes is the one that's unusual and not normal. In fact, if I take the other one, try to look at the context aspect, this is not true anymore. If I replace the NCC by the top correlated, top anti-correlated, or the top correlated, top not correlated, this time in absolute value, nothing there anymore. So the asymmetric classifier does something. So this is a bit of a weird experiment that's very indirect, but it's very indicative that there is a kind of a signal there.
Leon?
Yes?
Could you explain again what that score is again, the y-axis?
Yeah, in that one, the score is the context score, whether the feature is a context feature or not. Something that we know because we know the bounding boxes.
Oh, I see.
So the fact that we know the bounding boxes means that we're able to have the object feature or the context, the object score or the context score of the features. Now, the fact that the object score of the features matches so well what the arbitrary classifier a priori gives is very surprising.
But how did you define causal and anti-causal in each of these examples?
Well, by running the NCC classifier on the scores that are the features, on the scatter plot of the score of the features, score of the class. This classifier is the same for all categories. And the classifier was trained using mock causal data. So it's a strange idea. So for us, it means that, okay, well, we did that many times. We started in 2015, and we did it in 2016, and we did it again in 2017. We kept redoing that experiment with various setups. The one Robert was involved with was a different kind of a network, a different kind of object context classification. It was like that. And we changed it many times, and it's completely robust. So, okay, so we entirely have shown that the high order statistics is what NCC captures in image datasets can inform us about causation in the scenes, which is very unusual. But we don't know how to do it that well. And our detection method is completely cumbersome. Working with pairs of variables is a catastrophe. And if you look at all the pairs in a pool of variables, you're going to have a false discovery problem very quickly. But there is signal. There's a bush somewhere, and there is something in that bush. This is the way we look at it. So what's the next step? The next step is to wonder what kind of information are interesting. What is the thing we want to capture? And the thing that shocks me in this thing is this notion of cliff. Whether we look at confounding or direction of causation, it's always about cliffs. So basically, you have a shock in the data, for instance, because a uniform distribution stops brutally. And that translates into a cliff in the scatter plot. And also, if you want to find the causal mechanism behind some data, typically you want to find a simple one. It's going to be low dimensional, it's going to be quite small. So it has to do with what I call the mythical unsupervised learning, which is not about using unlabeled data to discover probability ratio. Like my typical example is a teapot. You have a teapot that rotates in all possible ways, but it's more often in a normal position. I don't care that my teapot is more often in normal position than upside down. What I care is that it rotates and that the set of images is homothetic to SO3. So it's about using unlabeled data to discover the causal generating mechanism. And I think the notion of structure, the structures that are important, cannot be separated from the notion of causation, because it's all about what can we do with that thing rather than compressing it. That's my viewpoint, at least, which is certainly different from Elad's. So what in the causal form? Corner, clips, shocks, lower dimensional causal model. So if we want to train low dimensional causal models supported by a small distribution, well, they don't have a density. If the distribution is supported by a low-dimensional manifold, no density. So you cannot reuse the density estimation unless you add some noise. And in fact, a lot of the generative modeling, the traditional one, is about transforming something low-dimensional, which is what we're interested in something that has a density by adding some noise model and working hard on the noise model, on the size of the noise, and then removing the noise and playing things with the noise. Well, in fact, the noise is an artifact of the fact that density estimation needs a density. So recently, there are a lot of work about the generator approach, where you have some observed data that follows a distribution. Then you start from a seed that follows a known distribution, you transform it, and you have generated data that follows the push-up distribution there. And this one has low-dimensional support because this is low-dimensional. And a low-dimensional distribution is the prototype of a cliff, it's a very sharp cliff. So I'm interested by matching cliffs. So if you want to compare distributions, so what you need to do this, in order to find theta, you need to define how you're going to compare these two distributions. And you can take the catalog of methods, and you have total variation, which is very useful for mathematics. In practice, it's a bit annoying. You have Kullback-Leibler, which is what's been used all the time in statistics, requires a density, so it's not going to be easy here. There are systems like the variational autoencoders where you add noise and you play the game of adding noise to get densities and be able to do Kullback-Leibler. You have Jensen-Shannon, which is the sum of Kuehlbach-Leibler opposite way relative to the mixture of the two distributions. So this doesn't require density. It's strictly between 0 and log 2. The way you can look at it is, in terms of information, is suppose you have two distributions, and you take the sum of the information in these two distributions, and you have the mixture. When you have the mixture, you lose the information about from which distribution the point came. So you lose 1 bit. And this is what this does. And then you have a whole series of so-called weak distance. The most common one is the Earth mover distance, which basically try to say how you're going to transform one distribution into another. So a distribution is a pile of dirt. You have another one, which is another pile of dirt. And you take your little truck, and you try to move the dirt in an optimal way to recreate the new one. So it's typically represented in that way. You say it's a minimum over all joint distributions that have marginals PR and PG of expectation over that joint distribution of the distance. So this represents how much of PR you have to move to PG. So X and Y, every X, Y point say how much you have to take from point X and move to point Y. And this is the cost of moving it. So in the generative adversarial network, I don't know if you know them. Do I need to explain?
Yeah.
I mean, we've been discussing it. Okay.
I can explain. Okay, I can explain. So you have this observed distribution, and you have the generated distribution here. And you're going to use a second learning machine called the discriminator. And the idea is that the discriminator is supposed to say whether the sample comes from the real distribution or the generated one. Ideally, if these two distributions are the same, the discriminator cannot say. If you can say, well, you know that it's not perfect. And the idea is to train the discriminator to recognize as well as possible whether it comes from the generated or the real one, and train the generator to make the task of the discriminator as hard as possible. That leads you to a saddle-bound problem where you have this cost function here, and the discriminator maximizes this cost function. The generator minimizes it. Is that clear enough? Yes, Ross?
That's a good question. So here, you talk about the generator generating the distribution, right?
Yes.
But then again, the generator is no noise.
Generate samples. Generator generates a distribution because when you apply, you give it inputs distributed according to Z, you distribute samples distributed according to a certain distribution PG that depends on the parameters of the generator.
But if your sample Z, if your Z space, your label space is, let's say, low dimensional,
Yes.
transforming into high dimensional, then what's the distribution?
It's still a probability distribution. It doesn't have a density. It's supported by a low manifold, or a low dimensional manifold.
Doesn't have a density.
It doesn't have a density.
So you can't evaluate it.
You cannot do Kuehlbach-Leibler. You can do Jensen-Shannon, you can do Earth mover. But anyway, the typical GAN, but the prototypical one, because this one, nobody uses that, in fact, search a saddle point of that kind. And it's a nasty saddle point. If you keep the discriminator optimal, it was shown in the GAN paper that minimizing L of phi star, which is the optimal discriminator for a certain generator, minimizes the Jensen-Shannon distance, assuming the discriminator is powerful enough. Now, if you do the opposite, you keep the generator optimal. Well, you have a discriminator. Discriminator makes a mistake somewhere. The optimal thing to do for the generator is to move all the mass there, which is obviously completely unstable. It's not going to learn. You have a bunch of other problems too, that if you do this, you keep the discriminator optimal. It turns out that the discriminator is very good at discriminating. Most likely, it's going to give you a very sharp answer, oh, this is real, this is generated. That means there is no gradient. When you backpropagate through this decision, nothing can tell you it's on the left or on the right. And maybe I should, So that's typically what's happening when you train the discriminator. The accuracy of the discriminator goes very high. The error of the discriminator goes low. This is log scale. And the gradient, so this is log scale again, keeps going down. the more you train the discriminator, the less gradient you have. So basically, you cannot train a GAN that way. The trick is not to train the discriminator too much and hope it's going to work. There is another trick, which is, again, in the paper, is that is change a little bit the way you train the generator, in fact. And you can show that this optimizes a kind of unholy mixture of Kullback-Leibler and JSD. But JSD with the wrong sign. It's a reverse Kullback-Leibler distance with a high mod dropping, meaning that if you have a multimodal distribution, you're going to abandon some of them, so you're basically memorizing. And you can also show that the gradients of that stuff under simple statistical assumptions about the gradients of each of them follows a Cauchy distribution. The gradients tend to go up. In fact, empirically, the more you train, the more the gradients are high. It's not very good either. Now, if you look at distributions with a low-dimensional support, let's take P0 and P theta, two uniform distributions supported by parallel line segments separated by distance theta. So I'm looking at degenerate distribution with low-dimensional support. And I look at my 4 distance. Total variation is 1 if there is a match, 0 otherwise. KL is 0 if there is a match because they're the same distribution, infinite otherwise. Jensen-Shannon is log 2 if they're different, 0 if there is a match. That's all discontinuous. Only Wasserstein in that category depends continuously on theta. So if my goal is to be able to map the support, I need a distribution that has this property. And that's called a weak distribution. Wasserstein is just one example of a weak distribution. There are a couple more. So if you want to optimize the Wasserstein distance, there is a trick about Wasserstein distance that's called the counter-rich duality. So let's go back to the track. So you have the distribution, you have the tracks, and they move things around. And suppose that you say, I want to give a price, I want to contract this to a track company, and the way I'm going to pay them is that I'm going to have different prices. A price where I sell the dirt to the track company, and the price where I buy the dirt from the track company. And basically, when you do it that way, there is a duality phenomenon that appears. You could prove it in a couple of lines. You just take 15 minutes and write it on the board, it's fine. And you show that the Earth mover distance is a maximum for all functions that are Lipschitz 1, or Lipschitz less than 1, of the expectation of the function under one distribution minus the expectation of the function under the other distribution. So the idea is, well, okay, we're going to parameterize f, for instance, with a neural network. We're going to enforce a Lipschitz constraint, for instance, by aggressively clipping the weights.
Can you approximate every Lipschitz function with a neural network?
No, you can't. You can't. It's going to be important. It's going to be important. You maintain f well-trained, and you train g theta by backpropagating through f. And the good thing is that no vanishing gradient, because if you do that, f should be close to Lipschitz 1, so the gradient is close to 1 through f.
I'm asking for a particular reason here, because what that really says is that the Lipschitz thing almost doesn't matter, right? Because in some sense, sure. But in some sense, by maximizing over some function class.
No, because if the function class is not Lipschitz, you're going to have the situation where you can have no gradient.
Sure, it could be a subset of Lipschitz functions, though, right?
Yeah, this is a subset of Lipschitz function. Yeah. So it's not.
That could be an example. Right?
Yeah, but you have to enforce a constraint to get Lipschitz less than 1 or less than a constant. Otherwise,
slope 1.
It's slope 1. You have to get force slope 1.
And then what is that linear with slope?
Right. Lipschitz constraint is enforcing slope to be less than something.
Yeah. No, I just say like, well, okay, keep going.
We're going to discuss that. In fact, this is related. What you say is related to something I guess Sanjeev is going to speak about. And I have a plug for him to use next time. I don't know if I'm allowed to talk about it.
Feel free, yeah.
Okay, so what's happening is that if you have a GAN discriminator, the normal one is something like this. Let's say, blue is the real distribution. Green is the generated one. The discriminator is like that red function. It's very good at discriminating. If you're here and look at the gradient through the red function, it doesn't tell you whether you have to go left or right. Now, if you force a function to be acting like a discriminator, but with a slope less than 1, and I don't know why Martin put an angle, because the slope should be 1, actually. Well, if you're here, you know you have to go left. and you have to move the generator left, which is sort of nice. And there is a theorem with a plug that basically, if you optimize f among the Lipschitz function, and you need some assumption about the boundedness somewhere, I forgot exactly where. So if you actually maximize f, when you backpropagate through f, you get the gradient of the Wasserstein distance. And the plug here is that these are expectations. In practice, we're going to maximize with a finite sample. We're going to get a number of true images or true data, and number of generated one, and do some gradient. So you want f to generalize. If you had all the Lipschitz one function, you wouldn't generalize. So the fact that we restrict to the subset of the Lipschitz one function that's parametric is super important there. And Lipschitz buys me that if I generalize, I get the gradients right too.
But there are two different things here, whether you generalize or whether you can find it with a gradient. And for generalization, it's enough that your class of discriminators have finite visit dimension.
Yes, but the Lipschitz one function are not.
Right. Well, no, but it's a sufficient condition.
Yeah.
But I'm saying that there are two different considerations, whether you generalize or whether you have a gradient and your algorithm will work.
The
Two things are separate.
Yeah, the theorem says that if you manage to generalize on f, you're going to get the right gradient.
That's not always the case. I mean, there are classes on which you will generalize and they will not have a gradient.
No,
Are you phrasing of Shai's question? It's also bothering me. So why can't I think of minimizing so the Weierstrass distance is actually well defined on the empirical distributions. Unlike the Hill distance, the Weierstrass distance is perfectly well defined and reasonable on the empirical distributions. So why can't I think of allowing all Lipschitz functions? I don't need to generalize because I'm only concerned with the empirical distribution now, and I'm still gonna minimize this Weierstrass between the empirical distributions, and then that's gonna be fine because I'm gonna generalize through.
Okay. We didn't know when we wrote the paper, but Sanjeev's going to tell you why you cannot do that. Cannot. You can if you make it parametric, essentially, and ensure that you can generalize through that thing.
Okay, I'll wait for.
So I can say it differently.
Exactly. I mean, yeah, that's it. Yeah. That's what you have to do.
You have to?
That's the theorem. Yeah, one theorem that I'm talking
about. So the thing that there is also a line of work. There is a line of work who advocate using Wasserstein distance for probability estimation, but not in that setup where you have degenerate distribution typically. And there is also a line of work of people claiming one is a bad idea. The main reason why it's a bad idea is that typically, if you measure the Wasserstein distance between a continuous distribution and a discrete approximation of a continuous distribution, this has horrible asymptotic properties. By horrible, I mean basically the error goes like n to the 1 over d. Absolutely horrible. Now, in my case, it's a bit different because I'm assuming my model is low dimensional, so d is small. And I'm interested in mapping the supports. So somehow, what I want to do is a bit different, but I recognize that in that work, we didn't qualify it very well. And there is still a lot to be understood properly there.
So question, how low is the dimension, you think, the manifold dimension?
In that one?
What do you think?
I think it was 100, which is very large already.
No, I mean for real images. I assume it's something like, is it like 50, 100?
I have no idea what's the size of a reasonable manifold for image. Also, I'd say that depending on your data somehow, if you don't have many points, you see just the gross features and you take the center of the gross features, you're going to find something simple. The way I like to see it is that if you're a child and draw a person for the first time, you're going to draw a head, a body, and 4 limbs. And that's it. Then you're going to become more refined. So somehow, I'm not sure that there is something about the real manifold of the data. I'm interested by the manifold of my model, and I want it to be low. So anyway, when we do that, we get something sort of nice. And don't get me wrong, I'm going to show you that in fact it's not that nice. It means that the old GAN was not nice at all. That the loss correlates with the sample quality. So one of the typical tasks for GANs is to generate images. And for example, images of bedrooms. And that's an interesting thing because when you generate images of bedrooms with GAN and you move the Z variable along a line, the changes you see in the images are not blurring the image of one bedroom to create another one. You see things that make sense, like moving the bed, moving the closet, changing the window, things like that, which is sort of interesting. So basically, when you measure the Wassersteinish distance, which is basically what you have when you optimize F, it's going, when it goes down, the image gets better. And whether you can use the MLP as a generator or you can use a convolutional network, both cases. But in both cases, we have to use a convolutional network for the F function, because if you use the MLP, nothing works. But at least the cost remains high. Now, if you do the same thing with the normal GAN, well, the loss that you measure from the saddle point problem, well, it actually increases. The image gets better. With the convolutional network, it increases slightly, the image gets better. If you use MLP as a generator, you just get garbage. And if you use MLP as generator and discriminator, well, the loss does crazy things and you get garbage anyway.
Well, on the last one, what does it mean that you have the previous slide? On the previous slide, you had the DC GAN. I thought DC GAN was the...
Okay, no, what I mean is the architecture of the generator. So it was that until now, there was no way to generate decent image with the MLP as a generator. And we can do it, basically, just because the training is more reasonable. And we can do plenty of nasty things with the generator. But discriminator are still to be convolutional and good. Otherwise, we get crap. But at least we know it. Yes?
So there's two things going on here, if I'm correct. One is to actually use Wasserstein type distance as a discriminator for GAN, and the other one is to actually define the ish in Wasserstein by using functions only that are outputs of CNNs. And so, Breton has this entire line of work where it uses kernels, for example, to constrain. So if you actually try to apply the CNN to compute distances or maybe Bayes centers or something as a class of functions, does it actually give you something extra when you're actually applying this to, say, image data sets, for example? So if you look at where to apply, right, so that's another constraint that you put on the...
I'm sure I understand the question. Can you?
Yeah, so I'm reformulating. So you take this soup over class of functions, which is now generated by a CNN, right? Rather than taking maybe something which is some RKHS or whatever.
No, what could be the RKHS is the discriminator.
Yes.
If you do MMD, you're going to have the discriminator or RKHS, which is interesting. Yeah. The kernel stuff is going to cost you a lot, but you can do it.
Yeah, so I'm not actually trying to think about the GAN itself. I'm trying to think about just isolating the new Wassersteinish distance that you've defined.
Yes.
So if I wanted to use this, using this building block, which is the CNN, can I actually gain something by applying the techniques that have been applied before using RKHS?
So what we know is that if you want to generate image, it's better if your discriminator is convolutional, regardless of the distance you use. If it's not convolutional, you get crap. At least with this one, it tells you it's crap because the cost is high.
Those are...
Yeah, that's the kind of bedrooms you get if your discriminator is not a CNN.
Things other than bedrooms with the MLP?
Oh, well, we tried plenty of things.
With the MLP in particular?
Oh, with the MLP?
Yeah.
I don't know. By now, a lot of people have used it and they know that. One of the problems that they have is that we don't have as much mode dropping, and we have to quantify that better. And because there is less mode dropping, you need more capacity in the generator, because that's to model more things. So if you're not careful, you're going to have less pretty images because the generator lacks in capacity. So there are other things you can do, is modeling choices, like for instance, that's the typical thing with everything convolutional, generator and discriminator, with Wasserstein, normal GAN, sort of okay. But now you start playing games with the batch normalization. You remove it, and Wasserstein still gives something okay, and the DC GAN approach, the normal GAN approach, just falls down. The typical GAN approach is very tricky. If you don't do the thing exactly like in the paper, it doesn't work. And you can do other things. Which one is that one? This one, MLP generator. That's with MLP. Forgot. But this is using MLP. Yes, that one is. Anyway.
Leon, can you interpret how is it possible that the MLP takes Gaussian noise and is able to reconstruct an image? Or?
It does.
How big is the training set of images? The bedrooms?
The sun data set. I don't know. I can find out. It's the normal one. We didn't change anything.
Million.
Or something like that. Yeah. So the first point, many authors advocated using Wasserstein distance to estimate densities for a number of reasons. The Rosasco in 2012, Couturier in France in 2015 in various setups. The MMD work of Gretton. We have this focus on low-dimensional support because this is what we wanted to do. The low-dimensional support is try to find small-dimensional mechanisms. And it's just the beginning. We're not there yet. And so my conclusion is that I'm completely convinced that there is a causal signal in the high moments that we can use and that we don't use nowadays. That takes the form of cliffs, corners, shocks, and in fact, that's interesting because the shock analysis or the discontinuity analysis is something that behavioral economists do when they want to look at causation. This has a lot to do with the mythical unsupervised learning. It's really about understanding the mechanisms that generate the images rather than the ratios of probabilities between two images. Weak distribution distance such as Wasserstein seem more able to catch it. But I would say Wasserstein is not the only one. And it has properties that are concerning. It's a bit of concern. And that's the beginning. That's my plan. This is what I want to do. I want to capture this kind of information in all kinds of data. Yes, Ross?
Just a quick question. So you've shown these examples that MLP can generate these nice-looking images. Is there any way you can use maybe Wasserstein distance to test generalization performance? How do you know that the model is not just memorizing training data, displaying it? In the sense of, is there any way, because you're working with low-dimensional support, I want to be able to take a test image and somehow say something about the test image.
Well, we still have the properties of interpolation. If you move Z along the line or continuous curves, you see displacement of things.
All of it is just visual, right? Is there any quantifiable way for me to say something about it?
It's unknowing. There is the one thing I would like to try is Joshua's experiment about modes, where basically you take an image and you take MNIST digits to create a three-digit number, and that's your distribution. And then you generate and you see how many of the 1,000 numbers you get.
But again, it's about eyeballing the result. I mean,
No. You can count. Because you know exactly that you generate something with 1,000 modes. And you can see how many you actually reproduce. You can actually recognize the digits if you want.
I'm not following. I mean, trivially wouldn't. I mean, it's just a product distribution. Right?
Yeah,
So you would have. I mean, I wouldn't expect it to fail. Would you?
well, I tell you, a normal GAN completely fails.
It fails.
Completely. The normal GAN is the reverse KL, is going to do a lot of more dropping. It's recovering less than 15%.
Out of those 1,000 digits.
Yep.
Oh, I didn't know that.
Completely fails. This thing, the alternate GAN thing, which is what everybody uses because otherwise it doesn't work, has this reverse KL term. So the GSD has the wrong sign, so it doesn't really matter. And reverse KL is going to give a high price if you generate something incorrect, but very low cost if you don't generate something that should be there. So the result is that you tend to drop modes, you tend to memorize more.
But in your case, do you find that it's also dropping the modes?
Well, I want to run the experiment. We find that it drops less. And by eyesight, when we generate, let's say, kitchens or bedrooms, we can see very well that the normal GAN generates the same bedrooms 2 times in our 10 by 10 grid, while we don't have that. But this has to be quantified. It's exact. That hasn't been done yet.
But this still doesn't mean that the model doesn't generalize. It's still very hard to test generalization performance.
The generalization of what? What do you mean by generalize here?
Like, how far, I mean, how much your model is memorizing the data? Like you're showing these bedroom scenes. Maybe they're all basically training examples, slightly twisted. You know, a little bit rotated.
Well, this is a problem with a lot of GANs, and the fact is that you have the interpolation property. You have the interpolation property.
I have a proposal, which
Yes.
maybe could help. So like the Epros group here has been doing a lot of this stuff where they call it conditional GANs, but it's also known as regression.
Yeah.
Where you have pairs of, if you actually have, rather than trying to make Gaussian noise look like images, you have images trying to look like other images. And so could compare the Wasserstein on these data sets, which are open to what they've done. Would that make you happy?
But a lot of it is still just eyeballing, right?
Well,
Look really, have you seen the cat stuff?
No, what I mean is that the experiment I liked was the Joshua experiment with this product distribution of MNIST digits, where you know the number of modes and you can see what you get. That's for the mode dropping. And for the bedrooms, I know that you can interpolate between bedrooms. And the database is not large enough that you have all the interpolations.
I think there's a huge gap here between practice and theory.
Oh, yeah.
Theory is we are running in parallel with pseudo-randomness. And pseudo-randomness is exactly about the same thing. How can you generate a distribution that looks like uniform from much fewer bits? So now you ask, how can I generate a distribution that looks like real life from whatever source that I have? Theory is very deep about it, but it doesn't answer the question of why would the person think that this is a bedroom or not a bedroom. But there are two communities here that address the same problem without hardly any intersection. So,
my goal here was trying to understand what kind of metric are able to find the features of probability distribution that are more likely to be interesting for finding low-dimensional structural models.
that we know a lot about, but it will not be the same as something that a human will tell you this looks like a bedroom.
Well, Russ is right saying that the GANs is a lot of a beauty contest. Or look at how pretty this image I can generate. And if you look at a lot of things like the generation of caption from images, it's also a beauty context. Look at the nice caption. And it's not very satisfying. I completely agree with that.
No, it's very satisfying.
Why? It's satisfying in the sense.
I mean, it's kind of amazing that you can generate photorealistic images. I mean, that's interesting.
Yeah, that's interesting. Yeah.
But wouldn't you want to, if you're really building a density model, wouldn't you want to take a new bedroom scene, right? And ask the model, what do you think about it? And your model to say, well, the probability of this as being a bedroom scene is actually pretty high. It's much higher than a random permutation of pixels.
And you don't have it. You want to.
It's one of these things where you and I just have this kind of difference in emphasis. You like probability distributions, and I don't.
No, but you want to apply Bayes. You want to apply Bayes rule. So what you want to do is say, because my model gives this density to this image, by reversing, I can say that the probability that this is indeed a kitchen knowing the pixel is such and such. But in that case, this is not really what you're modeling. In fact, when you try to model that, you have to do a lot of noise modeling, which is, I don't know, for me, noise modeling is the bane of generative models. It's where 90% of the energy goes. Usually you want to have a very small, simple model, and then you have to add all this noise on top so that it makes sense, and then you have to decide which noise, and you have to do the averaging techniques to address. It's just hell. Yeah.
Leon, one more question, then we should probably.
Just for fun, can you make the generator roughly invertible and then get a density for a new bedroom?
This has been done in a different ways, where you start a bedroom and try to generate the Z by optimization. And I don't know exactly what to make out of these results. Some people claim they were able to do it. What I can tell you. Yeah, until it's done in a way that's very robust. The problem is that the normal GANs, they're not robust at all. This one is a little bit more robust. I wouldn't say it's perfect.
Okay, we should probably stop there and go for break. Thank you very much.